Swayam Prabha. Digital India. Educated India.
This is lecture 8. In the previous lecture, we looked at nodal analysis, how to do nodal analysis when you have a circuit with current sources and resistors. That was the easiest case. And we extended that to when we have voltage sources. In that case, if you are doing hand analysis, you can use a super node. If you are trying to set up the equations for a computer, you can set the current through the voltage source as an extra variable and go ahead with the analysis. Now, when you have control sources, when you have a a voltage controlled current source, then all it does is to add some terms to the matrix, the conductance matrix, so that it becomes asymmetrical. Okay, and other cases can also be handled in the same way. Okay, when you have a voltage controlled voltage source, you will have to again either define a super node. If you are doing hand analysis, that's the preferred method because it reduces the number of equations. Or if you are setting up the equations for analysis by computer, then you define the current through the voltage source as an auxiliary variable and also write down the equation for the control source. Okay. So in all the cases, on the right hand side, you have the source vector, which consists of independent current sources and independent voltage sources. And on the left hand side, you will have a matrix times the variable vector. The variable vector will be the node voltages with respect to the reference node plus any auxiliary variable you may have used. If you have voltage sources, there will be the current through the voltage sources. Okay. Now, before we go on with today's lecture, if there are any questions on previous lecture or any aspect of nodal analysis, I would like to take them up. Okay, so looks like things were pretty clear. So what we will look at today is an alternative to nodal analysis that also is sometimes used, and that is known as mesh analysis. Okay. Now, the nodal analysis this uses KCL at n-1 nodes of the circuit. The circuit has n nodes and you have to write KCL at n-1 nodes, and variables are the n-1 node voltages and any auxiliary variables. And these auxiliary variables are currents through voltage sources. Okay. And the equations come from n-1 KCL equations plus equations for voltage sources. Okay. Now, the mesh analysis is the counterpart of this. Now, instead of starting with KVL, first I will tell you about something called the loop analysis. It uses KVL around b minus n plus 1 loops, okay, and it uses currents as variables, okay. Now, this loop analysis, the way it is done is you first identify a tree, then you add each link, that is branches that are not in a tree, to form a new loop. Okay. We took an example of this in one of the earlier lectures to figure out how many independent KVL equations are there. You have to first identify a tree, and then you add links to the tree to form new loops, and around each loop you write a KVL equation. Okay. Now this can be done, and this is a systematic way of doing it. What we will look at is a subclass of this, which is known as mesh analysis. Okay. So this loop analysis itself is quite general. Okay. And stop. Now the mesh analysis is a subcase of this loop analysis, and it's applicable to planar circuits. That is, circuits that can be drawn on a plane. Okay. So all the circuits that we have considered so far, they can be drawn on a plane. What I mean by this is without any branch crossing other branches. Okay. Now I'll give you an example. If you have a circuit like this, this is a planar circuit. No branch is crossing any other branch. Now, to this, if I add a branch like this, now this branch is crossing that branch. Okay. Now we have to be a little careful. It's not how you draw the circuit, but how it can be drawn. Okay. Because if I redraw this, even with this red branch, it can be drawn on a plane without any branch crossing any other branch. Okay. In this case, I have chosen to draw it in the middle, but if I draw it outside, then it won't be crossing anything else. Okay. So this is also a planar circuit. On the other hand, if I have something like this, let's say I have something like that, and then I also have something going from this node to that node. Now, if I have any branch between here and there, it has to cross some branch. Okay, I can draw it inside here, in which case it is crossing this branch. Alternatively, I could draw the same thing from outside, in which case it will be crossing this branch. Okay, so this circuit is definitely not planar. So the method of analysis that I will discuss today, mesh analysis, is not applicable to this circuit, but it is applicable to any planar circuit. Now I have to emphasize here that the general loop analysis, which is based on writing KVL in terms of the link currents, is applicable to every circuit. Okay, you first have to identify a tree and then go on. That is similar to identifying a reference node for nodal analysis. Okay, but this mesh analysis is simpler and it gives a structure that's very similar to nodal analysis, and that is what we are going to discuss. Okay. So once you have a planar circuit, so let me again take a circuit of this sort, and I will initially consider a circuit with only resistors and voltage sources. This is a planar circuit, no branch is crossing any other branch. And when you have a planar circuit, you can always identify regions like this, okay, loops like this, which are separate from each other. Okay, so imagine that you are looking at the map of India. Obviously, you will be able to identify states on the map, and each of the states will be separate from the other state. Okay, and everything will be on the plane. Now, each of those regions, each of the states, if you will, is called a mesh. So I'll call it mesh number 1, mesh number 2, and mesh number 3. Okay. So mesh number 3 is this loop, mesh number 1 is that loop, mesh number 2 is that loop. Okay. And let me call it V1, V2, R1, R2, R3, R4. Okay. Now, in each mesh, we identify a mesh current. Okay, let me call this I1 for mesh number 1 and I2 for mesh number 2 and I3 for mesh number 3. What I mean by this is that this is also a loop. Okay, so if I take it like this is also a loop, but inside this there is another loop. So that is something that we do not consider a mesh. Okay, so for a planar circuit, the definition is unambiguous. Each mesh is a loop that doesn't enclose any other loops. Okay, and with each mesh we can identify a current. Each mesh has a mesh current. Okay, and by convention we will take all of them to be clockwise. You can take all of them to be counterclockwise and you will get the same results, but our convention is to take all of them in the clockwise direction. Okay, and now the current in each branch can be written in terms of mesh currents. So the current in each branch is the algebraic sum, that is sum while taking into account the sign of the current. Algebraic sum of mesh currents. Basically, and which meshes do we take? The meshes that the branch is part of. Okay. So what I mean is, if you take this one, this branch is part of mesh number 1 and mesh number 3. So the current in this branch would be I1 flowing from left to right minus I3 because I3 is flowing from right to left. Okay. If you take this branch that is part only of mesh 3, so the current in this will be I3. Similarly, if you take this branch, it's part of only mesh 2, so its current will be I2, whereas this will be the current in this will be I1 minus I2 and so on. Okay. So is there any question regarding the definitions of the mesh and the mesh currents and branch currents in terms of mesh currents? Any questions? I defined planar circuits, meshes and mesh currents and branch currents in terms of mesh currents. Any questions about any of these? Okay, there is a question from Obaid asking how to find currents in each mesh. Now it's not something that we find yet. So far we have not solved for anything. It's a variable that you identify. Okay, I1, I2, I3. This is like assigning node voltages with respect to the reference node. We assign node voltages V1, V2, etc. all the way to Vn minus 1 and then solve for them. Similarly here we identify mesh currents I1, I2, I3, etc. for the number of meshes and then we solve for the mesh currents. Okay, so we have to find out yet what they are. Okay, so now the branch currents must be pretty clear also. Okay, just so that it's very clear, I will write that current here is I1 minus I3, current here is I1 minus I2, current here is I2 minus I3, and current in this direction would be I3 alone. Okay, and here it is I2 and here it is I1. Okay. Now, once we define the mesh currents and find the branch currents in terms of mesh currents, we can write KVL around each mesh. Okay. So, if I write KVL around mesh number 1, and let me call this V1. And this is V2. If I write KVL around mesh number 1, what do I have? the voltage drop across R1 plus voltage drop across R3 equals V1. Okay. And the voltage drop across R1 is R1 times the current in R1, which is I1 minus I3, plus R3 times the current in R3, which is I1 minus I2. And that's all. That's all the resistors we have. And we have an independent voltage source. And just like we put independent sources on the right side in nodal analysis, we do the same in mesh analysis. And if you look at the direction of this, I1 minus I3 times R1 is the voltage drop in this direction. I1 minus I2 times R3 is the voltage drop in that direction. So the sum of this plus this equals V1. Okay, because V1 is also in the same direction. Okay. So now for the second mesh, what we do is the same. The voltage drop across R2 in this direction is R2 times I2 minus I3. Now we always go clockwise around each mesh, and we also take the voltage drops in the same direction. Okay. So for this particular branch, the one in the middle, we also take a voltage drop with this to be positive and that to be negative. Okay. Maybe I'll erase some of these things. So while writing the equation for the second mesh, we take the drops in that direction. Okay. While writing the equation for the first mesh, we take in this direction, for the second one in that direction. Okay. And for the third one, again, we would do it in the clockwise direction. Voltage drops in the clockwise direction, like that, and like that. Okay. So this is just convention. Even if you write it the other way around, you will get the right answers. But if you follow this convention, you will be able to if you follow this convention, the equations will come out in a systematic manner. Okay. Now, one of the participants has raised hands, but I think unfortunately today's audio setup is such that I cannot hear your questions. So whatever questions you have, please type it in the chat window. So here the voltage drop across R2 plus voltage drop across R3, which is, if you look at it, it's the current in this direction times R3, okay, which is, and it is equal to minus V2, because if you look at it, this voltage drop is here to there, that is from here to there, and that, if you look at V2, it will be minus V2. Okay, if you look at the appropriate direction. Or alternatively, you can think of this voltage plus that voltage plus V2 summing to 0. So that means that when you shift V2 to the right hand side, you will end up getting minus V2. Okay. Now finally, for the third loop, the voltage drop across this plus the voltage drop there plus the voltage drop there equals 0, because there are no independent voltage sources in the loop. Okay. So R4 times I3, that is the only current flowing through R4, and for the voltage drop in this direction, I have to take the current in that direction, which is I3 minus I2 plus R1 times I3 minus I1, and this will be equal to 0. Okay. And this is the equation for mesh number 1, KVL equation around mesh number 1, mesh number 2, and mesh number 3. Okay. So I hope this is clear, the procedure for writing the KVL equations around the mesh. So what you do is, you identify mesh currents, then you represent each branch current as a sum of two mesh currents. When I say sum, it's the sum with direction, so it will come out to be the difference between two mesh currents. Okay, and uh, then you write out the KVL equations in terms of the mesh currents. Okay. Now, where you have resistors, you will have current times the resistance value, and the current is written in terms of the mesh currents. Okay. So you will always have terms like I1 minus I3, that is the difference between two currents times the resistance. That will be on the left hand side. And on the right hand side, you will have any independent voltage sources in the circuit. Okay. Now there was a question from Rajesh asking what is the difference between a mesh and a loop. Like I said, mesh is also a loop, but it doesn't contain any other loops inside. Okay. For instance, in this particular circuit, this is a loop and this is also a loop. But the second one is not a mesh because that loop contains a smaller loop inside. Okay. Hopefully that is clear, whereas this is a mesh. So every mesh is a loop, but every loop is not a mesh. Okay. And regarding the direction of mesh currents, like I said, by convention, you always take each mesh current to be in the clockwise direction. Okay. Now that gives you a nice structure because so let's say you have two meshes. I'm not showing the elements. I'm just showing the branches in an abstract way. So you take a current like this, I1, and take a current like this, that is I2. Now, every branch current will be equal to either one mesh current or the difference between two mesh currents. So this branch is common to the two meshes, and in the left side mesh the current is going downwards, and in the right side mesh it will be going upwards. If you choose all your mesh currents to be in the clockwise direction, this will always happen. Okay. So every branch current can be written either as a mesh current, a single mesh current, or as a difference between two mesh currents. Okay. And this is analogous to if you assign node voltages, every branch voltage will be either equal to some node voltage, okay, if the branch is between that node and the reference node, or it will be the difference between two node voltages. Okay. Is this fine? So these are the equations in terms of the mesh currents, and I will again rearrange them and group the variables together. So I'll have I1 R1 plus R3 minus I2 times R3 minus I3 times R1 to be equal to V1. That is the equation for mesh number 1. And the equation for mesh number 2, that is minus I1 times R3 plus I2 times R2 plus R3 minus I3 times R2, that will be minus V2. And similarly for 3, we'll have minus I1 times R1 minus I2 times R2 plus I3 times R1 plus R2 plus R4 equals 0. Okay. So these are the mesh equations. Now let me copy over the mesh equations also.